Okay, so yeah, chapter 11, as I said, or module 11 from Introduction to Networks, IPv4 addressing, and yes, it's very central to the course, this particular module. Okay, so we're going to look at the IPv4 address structure. We're going to have a look at IPv4 unicast, broadcast, and multicast packets. We'll look at different types of IPv4 addresses, so public and private, and also other addresses that are reserved for other users. We're going to look at segmentation, and so by subnetting we can actually improve both performance and security for networks. And then we're going to talk about how we actually do the subnetting process. So, of course, the first part of the chapter is looking at the IPv4 address structure. So, I think we have mentioned this in the past, but of course, yeah, so basically an IPv4 address is a 32-bit hierarchical address that is made up of a network portion and a host portion. When determining the network portion versus the host portion, you must look at the 32-bit stream. A subnet mask is used to determine the network and host portions. So as we can see here in this example, we've got a network number of 192.168.10, and then the host portion means that it's host 10 on that network. So to identify the network and host portions of an IPv4 address, the subnet mask is compared to the IPv4 address bit for bit, and I actually demonstrated this on the board previously, and so it's called ANDing or logical ANDing. And so as you can see here, the subnet mask is a string of ones followed by a string of zeros, and so it's actually through this process that we can calculate the network address. And so remember, wherever there's a column with two ones, the end result will be a 1. Wherever there's only 1 or 0 ones, it will always be a 0. And so, of course, basically in this process, wherever there's a 1 in the subnet mask, the value from the IP address will carry down. Wherever there's a 0 in the subnet mask, it will always end up being in all zeros. So the prefix length is a less cumbersome method used to identify subnet masks. So of course, a subnet mask, like the previous example here was 255.255.255.0. So of course, translating that into binary, it's 24 ones followed by 8 zeros. And so a way to describe that, instead of having this mask here, which is the same as the previous slide, we can just say the prefix length is 24 bits. And so what it's saying is the first 24 bits of that address are network number. And so, of course, that ends up being exactly the same as what the previous slide said. So prefix length is just another less cumbersome way of writing it. You can write it in 2 characters instead of lots. And so it is written in slash notation, therefore count the number of bits in the subnet mask and prepend it with a slash. And so that's what they're saying here is, with this one, you can count the ones here. There's 24 of them, so you do slash 24. And the slash is there just because you often write the IP address slash 24 all in one string of characters, and the slash is just a delimiter so you know that the IP address is finished here and the prefix length is here, basically. All right, so with logical ANDing, how do we go through that? As I said, I did demo this previously. So a logical and Boolean operation is used to determine the network address. Logical AND is the comparison of 2 bits where only a double 1 or 2 ones will end up with a 1 as a result. And any other combination ends up in a 0. So, of course, with 2 bits, there's actually 4 possible combinations. So they could both be 1s, they could both be 0s, and of course, one could be a 1 and the other one a 0, and of course, those could swap as well. And so they're the 4 possible ways that it can end up. But anyway, so to identify the network address, the host IPv4 address is logically ANDed bit by bit with the subnet mask to identify the network address. And so, as I said, because the mask here in this last 8 bits has got 0 in every column, the last 8 bits will always end up being a 0. And that's why the network address is always expressed as a 0 in the host section. So 192.168.10.0, that's the network address. That's what the router uses and what it shares with other routers to advertise that network number. Now, network host and broadcast addresses. So I just spoke about the network address. And so, of course, a network address has all zeros in the host bits. Now, I think we might have mentioned it before, but you can have a directed broadcast or a subnet broadcast address, and that is actually all ones in the host section. And so, of course, with the example we've been using with this 24-bit mask, the last octet would all be ones, because that's all of the host section. And so 192.168.10.255 is the broadcast address for that subnet. And then all the numbers in between, so starting out with number 1, of course there's 256 possible addresses because, well, host addresses in this subnet, because you've got 8 bits. 2 to the power of 8 is 256. But because we've got a network address that can't be used by a host, and we've got a broadcast address that can't be used by a host, we actually have 254 possible hosts on this subnet. So the actual formula to figure out how many hosts on a subnet is 2 to the n minus 2. So in this case, 2 to the 8 is 256 minus 2, 254. And as you can see here, the range of addresses is 1 through to 254. So that does pan that out. If you've got a larger subnet, so let's just say it's a B-class address, you've got a 16-bit mask. And so, the first 2 octets are network number, the last 2 octets are host number. You've got 16 bits. 2 to the power of 16 is 35,536. There's still the network number, there's still the broadcast, so minus 2, and so that's actually how many hosts that network would have. And so, of course, smaller networks will again be 2 to the n minus 2. And so they're the 3 major types of addresses, at least when it comes to subnets. And so there's a network address that's used by the router and advertised to other routers. Host addresses are, of course, assigned to hosts. And the broadcast address is basically all hosts on that subnet. Now, there's unicast, broadcast, and multicast packets that can be sent. And I think we might have covered this with layer 2 as well. And so it all matches pretty much the same. And so unicast transmission is sending a packet to one destination. There's only ever one source address. And so one source to one destination is a unicast. And so for the example here is 4.1 is sending it to 4.253. And so just that's where it goes, that's it, done. And so that's your normal communication is normally via unicast. Now, broadcast is sending a packet to all other destination IP addresses. For example, the host 172.16.41 sends a broadcast packet to all IPv4 hosts. Often it will actually be 32 ones. And so we've spoken about ARP in previous chapters. That was the destination used for ARP. And so other protocols also use broadcast to discover information, and typically that is the destination address. Of course, the source is still only ever one, so it's one source to all other destinations. Now that is actually all other destinations on the same network, because routers rarely, if ever, you would have to configure it to pass on broadcasts, but typically they do not. And so the router will not send that broadcast any further. It will just stay within that subnet. And so a sort of a compromise between the two is a multicast. And so a multicast is to a group And so there is actually a protocol called IGMP, which is Internet Group Management Protocol, and that's actually how you join one of these multicast groups, is through IGMP. And so, for example, 172.16.4.1 sends a multicast packet to this multicast group, and so there is actually part of the IPv4 addressing range set aside for multicasts, and so this is one of them. And so 224.10.10.5 is the address that's been used. And so, as you can see here, these two laptops are interested in that multicast message, but the printer and the other host are not. Now, whether all of the other hosts will see it or not actually depends on how smart the switch is. Some switches will actually listen to IGMP messages, which is what these two hosts would have sent to join that multicast group. And the switch would have taken note that, oh, okay, these two hosts are a member of this multicast group. I'll only forward the packets to them because they're the only one interested. So these won't even see it. But if it's a less intelligent switch, multicast will actually go to all hosts. But these hosts will actually be able to ignore a multicast a lot easier than they can ignore a broadcast. And so the NIC will actually go, oh, I'm not interested. Okay, so types of IPv4 addresses. So, back in the early 90s, when they figured out that the addressing space was running out, they decided to separate some addresses away from the flock, basically, and turn them into private addresses. And so RFC 1918, has anyone heard of an RFC before? No? Actually stands for request for comment, and that's actually how new internet standards come out. Someone has a bright idea, writes an RFC, and then of course other people will comment whether that's a good idea or a bad idea, or maybe you could do it this way. And so that's actually how standards come about. And so I think it was part of the IETF that actually created this one, I'm not sure though. And so basically they said that these three ranges of addresses can actually be used by anyone, as opposed to actually having to register them with ICANN. And so you can use them anytime you like. There is a proviso though, you cannot connect to the internet with them. And so private addresses are common blocks of addresses used by most organizations to assign IPv4 addresses to internal hosts. So if you look at your own IP addressing on your machine here, it's actually got a 10 address. And so you've got a private address on your computer here. And of course at home, my guess would be that your computer has an address 192.168.1 dot something. Well, that is in the range as well, because all 192.168 addresses are private. And so that's what your computer at home will have. And of course, the way that you can connect to the internet is your router does NAT, which I think we've mentioned at least briefly previously as well. Network address translation. We actually will go into more depth later, but yeah. And so private addresses are not unique and can be used internally within any network. However, private addresses are not globally routable, which means you can't connect to the internet. ISPs actually should block every packet that has a source or destination address of those ranges. That was only one. Yeah. So routing to the internet. Network address translation translates private IP addresses into a public IP address. NAT is typically enabled on the edge router connecting to the internet. It translates the internal private address to a public global IP address. And so basically, this is like our homes here. I suppose more specifically this one. And so our home router will have gotten one address from our ISP, one public IP address. Of course, we've got all of our hosts inside the network having private IP addresses. And so when they send a packet to the router aimed for the internet, be that Facebook or Cisco or Google or whoever it might be, this router will then look at it and go, okay, well, I'll actually translate that source address from 192.168.1 dot something into whatever the public IP address is that I've been given by my ISP. And then it will just make sure that the port numbers, which are layer 4 are unique, so it can keep track of that conversation. So if it needs to, it will actually change the source port number so it can keep track of different conversations. And so that's how it works. As I said, we will go into more depth into it later. And so that's basically how NAT works. And NAT is the major solution that has actually gotten us from the early 1990s until now, still being able to use IPv4. There are some problems with it, though. It's not perfect. Now, there are some other special use IP addresses out there that can't be assigned to hosts. And so we've spoken about the loopback address before, I assume. You can ping yourself with 127.0.0.1. If I haven't, well, you can. Also, if you're sitting at a web server and you want to see what web page is on your machine you're sitting on, you can actually type 127.0.0.1 into the browser, and it will actually talk to its own web server and load the page that's on your computer. So basically, the loopback address stays within that host. And so you can use it to test if TCP/IP is operational, but you can also use it to talk to local services as opposed to network-based services. And so, yeah, the example here is pinging yourself, and that's just to make sure that your TCP/IP software is working properly. Don't often have problems with it. It's pretty reliable these days, but anyway. Now, link local addresses. Another name for it is a peeper. Has anyone ever booted their Windows machine and it's had a 169.254 address and it can't talk to anyone else? Okay. Well, you haven't had a DHCP server fail at home, apparently. So basically, what that is used by Windows DHCP clients to self-configure when no DHCP servers are available. So if the DHCP server on the network is unobtainable, and that's actually happened in this building a few times, because at one stage at least, the DHCP server was not in this building. And so our DHCP requests actually went via a fiber link to a different campus, and the server there was dead, and so the entire building was getting 169.254 addresses. And yeah, couldn't talk to the internet, could hardly talk to each other. So basically, it's called a peeper, automatic private IP addressing. And so basically, when it sends out a DHCP discover message and gets no replies at all after a certain amount of time, Windows will then basically use this as the first 2 octets, and then it will do some a randomizing number for the last part of the address, and it will then assign that to the host. And so the point of that is so that hosts on the same network can actually talk to one another in a very basic way. And so not all communication is dead. You can't talk to the rest of the world, but you can at least talk amongst yourselves a bit. And so that's what a peeper or link local addresses are about. When it comes to IPv6, it's actually a lot more common, and there's actually addresses. If you ever see FE80 as an IPv6 address on your machine, that is your link local address. And so, yeah, IPv6 does something similar, but it's better implemented, basically. Okay, now, back in the dark ages, there used to be 5 classes of IP addresses. They still sort of apply, but less strictly now. And so RFC 790, so it's a long time ago, as it says 1981, they define the addressing as A class, B class, C class. They're the ones that can be assigned to networks and hosts. D class is the multicast range, and E class, they call it experimental, which in reality means they don't know what to do with them. And so basically, as you can see from this pie chart, half of the address range went to A-class addresses. And so you can see here that the range is quad 0 through to 127. 255, 255, 255 actually is the last A-class address. Now, there's a couple of provisos with the A-class addressing. We've already seen that 127 is used, isn't it? That's how you ping yourself. That's that link local address. So that's 16 million addresses not available. But anyway, Also, you can't actually use network quad 0 because that's deemed to be that number there, all zeros, is actually deemed to be the entire internet, sorry. And so that is actually used for a default route, quad 0. And so that's another 16 addresses you can't use. So 16 million addresses, I mean. So, a bit of a problem. B class is basically 128 through to 191. C class is 192 through to 223. And if you remember that example of the multicast a few slides ago, it had a 224 address. Well, that is the multicast range. And so from 240 through to 255, that's 16 times by 16 million addresses that can't be used. Glassful addressing wasted many IPv4 addresses. That's true. Now, people saying, oh, if they hadn't done that, we'd still be able to use IPv4. Not really, because in the last months before the IPv4 address space was depleted, every month there was an A-class address worth of addresses. So 16 million addresses were being used every month. And so there's a few months in it. So it's not really that big a problem. 4 billion is just does not get divided by 7 billion people very easily. So yeah, it was always going to be a problem. Now, classful address allocation was replaced by classless addressing, which ignores the rules for A, B, and C. And so I've actually had quite a few A-class addresses assigned to my house at home at different times. I didn't have 16 million addresses, that's for sure, because it was all subnetted and I got one of those A-class addresses. And so the actual rules on how these A-class numbers are actually assigned is actually down to the binary. And so A-class addresses, in the first octet, the first bit is a 0. And so that's what 0 through to 127, because they're all less than 128, aren't they? And so that's how that works. And then B class, the first 2 bits are a 1 and a 0. And so that's why it's 128 through to 191. C class is 110. So that's why it's 192 to 223. D class is 1110. And then E class is 1111. And so that's why those strange boundaries are made up, is because it is actually binary that was used to divide the classes. And so basically, back in the old days, they could just look at the first octet and go, oh, okay, oh, that's got a 0 for the first bit. Well, that subnet mask is, well, that's an A-class address, and so that's got 16 million hosts, that address. And it knows how long the address is because it was an 8-bit address for the network. B class, of course, it was 10, and so, oh, okay, yeah, the network address is 16 bits long, and so there's 16 host bits, and so on. And so that was how they used it. It was very easy for the routers to pick it up, but decidedly inflexible. Okay, so how do we get IP addresses? And so there's an organization called IANA, Internet Assigned Numbers Authority, manages and allocates blocks of addressing, both IPv4 and IP6, to the 5 regional internet registries, so RIRs. So of course we're in Australia, and so we're part of APNIC, and so you can see the purple color code for them. And then there's other ones, so ARIN, which is Northern America, LACNIC, which is Latin America, AFRINIC, of course, is Africa, and then there's RIPE, which is, I think it's Asia, it's Europe, the Middle East, and parts of Asia, basically. Okay. Can't remember exactly what the acronyms stand for, but yeah. All right, so now we're up to network segmentation. Now, broadcast domains and segmentation. So many protocols use broadcasts or multicasts, for example, ARP, to locate other devices, hosts, send DHCP discover broadcasts to locate a DHCP server, and so on. Now, switches always forward broadcasts out, and so when a broadcast arrives at a switch, the switch will send it out all other interfaces except, of course, the one it arrived on. The only device that stops broadcasts is a router. As I said earlier, routers don't pass on broadcasts. Each router interface connects to a broadcast domain, and broadcasts are only propagated within that broadcast domain. So basically, every interface on a router is a broadcast domain. Now, large broadcast domains are a problem. And so basically that these hosts can generate excessive broadcasts and negatively affect the network. The solution is to reduce the size of the network and create smaller broadcast domains in a process called subnetting. So dividing the network address 172.16 into two subnets of 200 users each would work better. And so instead of having one broadcast domain for everyone with 400 users, we have two broadcast domains with 200 users each. And so that halves your broadcasts, and it does actually make things a lot more efficient. So reasons for segmenting networks. So subnetting reduces overall network traffic and improves network performance. It can be used to implement security policies between subnets. It reduces the number of devices affected by abnormal broadcast traffic. And subnets are used for a variety of reasons, including different locations, groups or functions within an organization, or different types of devices, but it's probably less rare and less common, I mean. So you might have a subnet per floor in a building. Depends on what the building does. That might work well. Or, of course, you might have different subnets for different uses. So, like in here, we've got, we're in a classroom here. We are not on the same subnet as what my machine on my desk is on in this building. And so here, of course, they've got examples of administration, human resources, students, and accounting. So basically separated by function. So how do we subnet an IPv4 network? This is the tough bit. Now, networks are most easily subnetted at the octet boundary, so /8/16 and /24. Note that using longer prefix lengths decreases the number of hosts per subnet. So let's actually I might bring up the command prompt. Here we go. I'll do ipconfig. I don't need all. Now, these are the details for my computer on this network. Now, if you remember earlier slides, the 10 network, there's a couple of interesting things about that, isn't there? So I already told you one, it's a private network, isn't it? So I can't connect to the internet with that IP address without someone doing address translation for me. And yes, TAFE does do that. And another thing, what type of address or class of address is the 10 network? Did someone say something? A? That's correct. It's an A-class address. And so if you remember A-class, well, that's its default host mask is /8 or 255.0.0.0. But my subnet mask is not that, is it? I've actually got a 24-bit mask. You'll have the same. I'm assuming we're on the same subnet. And so what TAFE has done is, because, as we said here earlier, if you've got a default A-class mask, you've got one network with 16,777,214 hosts. That's a lot of hosts. And so the previous slides, when it was talking about segmenting networks, it was saying you might segment 400, subnet with 400 hosts into two with 200. Well, a subnet with 16 million hosts, that would be god-awful to be connected to. You wouldn't get anything done. Everything would be broadcast. Nothing would be actual traffic moving. Nothing would be achieved. And so what the administrators have done for our network is they've actually chopped it up into a whole pile of subnetworks. And so instead of it just being an 8-bit mask, they've stretched it to be a 24-bit mask. And so instead of that being the network number, now that is my network number. And so here, they've actually left the second and third octets to be parts of the network number. And so what's 2 to the power of 16? That's 65,536 possible subnets. Now, I don't think TAFE is going to use all of those, but it gives them a bit of flexibility. And so with that, basically, that's how we get all our subnets in the organization, is by having a different subnet for staff, students, HR is probably separate, I'm assuming, and of course, IT support and things like that. So that's how we all get different subnets. So that's why I've used the 10 network, because it's just lots of room to move. And if you need to redesign things, you don't actually have to reinvent the entire network. You can just add another subnet quite easily. So that's why they've done that. And so basically, that's what they've done, is they've subnetted this /8 into a /24. And so each subnet has 254 hosts. So at the most, you'd get 10 classrooms per subnet. That's all right. But yeah, they're smaller subnets. Broadcasts are less of an issue. And so it does work nicely. Now, so as I said, if it's a B class address, /16 is the default prefix. And so you've got 65,000 odd addresses. And of course, with the /24, you've got 254. Now, so they're the A, B, and C. But of course, you can modify these by subnetting quite easily. And so, as I said, that's what TAFE has done. Now, here's an example of what you could do with the 10 network addressing scheme. And so what they've done is basically they've done some subnetting here, and on the second octet, they're actually separating them there. Now what they're doing is they're actually sort of, if you look at the second lot here afterwards, basically what they're doing is this range of addresses could be for Adelaide campus. The next range of addresses could be Noarlunga campus. The next one could be, Tonsley campus, and so on and so forth. And then within that range there, with /16, you've still got 65,000 addresses available, or 256 subnets of 254 hosts. And so here, that's how you could actually have all your different subnets for all your different classrooms and staff groups and all kinds of things like that at a different campus. And that's what they're explaining here, is this is sort of a top level division, so middle management basically, and then the next one is lower management. And so it's the tree structure of the addresses basically. And so these are subnets of a subnet basically. So that's what they're suggesting as a possible solution. And with an A-class addressing scheme, as I said, there's lots of room to move. And so here, so you've got up to here 256 possible campuses, each with 256 subnets with 254 hosts per subnet. And that's still very tidy, still on the octet boundaries, very nice and easy to do. And now, subnetting within an octet boundary. So you can actually subdivide a C class into smaller subnets as well. Now it gets uglier. It's a bit harder to figure out with your head, but it does work just as well. The computer actually doesn't care, because that dotted decimal notation, that's only done as a last step to display to us humans. So basically, if you've just got a C class addressing range, you can actually divide it into multiple C class ranges. Smaller ranges, sorry. And so here, instead of /24, we've got /25. You can actually have 2 subnets with 126 hosts each. If you divide it again, you can have 4 subnets with 62 hosts. If you divide it again, and so on and so on. So basically, as you can see here, what we're doing is we're borrowing a host bit to use as a network bit. So instead of /24, the mask finishing here, we've just borrowed an extra bit here. And so now this has two possible values, 0 or 1. That's how you get your two subnets. Here there are 7 bits left. 2 to the power of 7 is 128, minus the subnet number, minus the broadcast number. 126 hosts can use those two subnets each. So here, if we borrow 2 bits, again, the network number is 26 bits long instead of 24. And so here we can count, we've got 4 possible bit patterns, 00, 01, 10, and 11. There's 4 bit patterns available, so there's 4 subnets. Now, because we've got less host addresses, we've got 6 bits. 2 to the power of 6 is 64, minus 2, 62 hosts, and so on. So basically, you can design your subnets to be the size that you need them to be. And so this bottom one here, you can have 64 possible subnets with 2 hosts each. And so because we've got 6 bits that have been borrowed, we can have 64 possible subnets. There's 2 bits left, and so 4 possible bit patterns, but of course we've still got the subnet number, we've still got the broadcast, so there's the 2 left in the middle that are the usable host addresses. You can't have a mask longer than /30 in an IPv4 address, because if you had a /31, you'd have two addresses available. One's a subnet number, one's the broadcast. There's actually no host addresses, and so it doesn't achieve anything. So that's why /30 is the longest. Now, it's sort of basically, how do we make these decisions? So, all right, we're going to go through subnetting a /16 and a /8 prefix. These are the easier ones. So, we've got a /16 address. And so, basically, so we start out with the first 16 bits being host network number, and the last 16 being host number. So that's one subnet with 65,534 addresses. If we borrow an extra bit, of course, there's 2 possibilities. You've got 2 subnets, each with 32,766. To the power of 15. 65 then, yeah. All right, so if we borrow 2 bits, again, we've got 4 possible subnets, still with 16,000 hosts. That's a good number of hosts. Too many, probably. Borrowing 3, and so on and so on and so on. So basically, you can do this lots of times. Again, the longest mask possible is /30. So one thing I didn't show us, didn't highlight at least, was the mask for a /30 is 255, 255, 255, 252. So the last 2 bits are left as zeros. And of course, that's 2 and 1. If you subtract 3 from 255, that's why it's 252. Okay. So how do we, now that's all very fine. That's certainly some ideas, but sort of that's not the process you would normally go through to do subnetting. That's a long and arduous process, figuring all that stuff out. It's when we start using the formulas that's actually the faster way of doing it. So consider a large enterprise that requires at least 100 subnets and has chosen the private address range of 172.16.00/16. The figure displays the number of subnets that can be created when borrowing bits from the 3rd octet and 4th octet. Notice that there are now 14 host bits that can be borrowed. You can't use the last 2, as I said. To satisfy the requirement of 100 subnets, you need to borrow 7 bits. So basically, we use the formula. So basically, you just do a whole pile of what ifs. So as I said, when it comes to subnets, you do 2 to the power of n, and n is the number of bits we're going to borrow. And so we need 100 subnets. Let's try 2 to the power of 5. So what's 2 times 2 times 2? 5 times. That's actually 32. Oops. Oh, so why did I write 36? 32. So not enough. So if we do 2 to the power of 6, every time you add 1 to the number, you're doubling the number of values. So we're up to 64, getting close. Not quite there though, are we? And so 2 to the power of 7 is 128, which is more than 100. So we'll get 100 subnets and we'll have 28 spare, just in case of any future expansion. And of course, if we use 2 to the power of 8, it's 256 possible values. And so basically, you just need to do this math to do it. You don't need to do the big tables that were being done before. And so that's basically what we're doing here. 2 to the power of 1, of course, is always itself. And so, as you can see, 2 to the power of 7 gets you 128. And so that's how we come up with borrowing 7 bits. Now, of course, it started out as being /16 plus 7. And so, well, 16 plus 7 is going to be /23. All right, so now we're using a different example. How do we calculate that we want 1,000 subnets? So this is an ISP apparently. And so it's clients using the network address 10, good idea, which means there are 8 bits in the network portion and 24 host bits available for you to play with. So the figure displays the number of subnets that can be created when borrowing bits from the 2nd and 3rd octet. Notice that there are now 22 host bits that can be borrowed. To satisfy the requirement of 1,000 subnets for enterprise, 10 bits need to be borrowed. And so you would, for the typo, it'd be 1,024 subnets. So remember I said when we talk about a kilobyte, it's not 1,000, it's actually 1,024 because it was 2 to the power of 10 is 1,024. So that's a very quick way of getting to that answer. So I did up to 8. Basically, you just double it again for 2 to the power of 9, 512, double it again, and you get to 1,024. And so from it being a /8 would now need to be a /18. And so that would, so basically, yeah, as you can see here, these 10 bits would need to be borrowed. So instead of being /8, it would be /8 plus 8, 16, plus the other 2 would be /18. Okay, subnet to meet requirements. Now, when you're figuring out an addressing scheme for an enterprise, they will have certain needs. And so of course, the intranet is their internal network. And so from there, typically we use private IP addresses inside organizations these days. And so one possible network you would need is a DMZ. We've all heard of a DMZ, have we? Demilitarized zone. No South Koreans here or North Koreans. It's the most famous DMZ. So basically, it's implying that this is no man's land. But what it really is it's actually an area of your network that's accessible from the outside world. So if you've got a web server, you might put it there. If you've got an email server, you might put it there. DNS server, another example of something you might put there. Now, because it's accessible from the outside world, you internally don't necessarily trust it because it could be attacked. But yeah, it of course is under your control, and it's your web servers, your external facing servers, basically. And so the DMZ either might have public IP addresses assigned to the devices, or this router/firewall might actually do NAT for them in a static fashion. They'll always have the same external address, one or the other. But anyway, don't have to worry too much about that. And so, of course, within that within the private network, well, there's going to be servers. You might have a separate subnet for them. And again, within that private network, you might divide it up into departments. So accounting and HR and, you know, other staff, sales, whatever it might be. Okay, so there are two considerations when planning subnets. So how many hosts do you need in each network? And how many subnets do you need? And so that's the two things, and they are often competing requirements. And so in that previous plan, you know, whether you have your internal addressing there as well as here, and so you've got to figure out how many subnets you need, and of course, how many hosts in each of those subnets. Now, in this example, corporate headquarters has been allocated a public IP network address of 172.16 by its ISP. That's not very public, but well. And so it's /22. And so they've got 1,022 usable addresses. There are 5 sites and therefore 5 internet connections, which means the organisation requires 10 subnets, with the largest subnet requires 40 addresses. It allocated 10 subnets of a /26 subnet mask. So, /26. And so /24, you've got 254 possible hosts. /25, you halve that, so it's 126. /26, it's going to be 62 hosts per. Now, it's all these powers of 2. You can't actually create a subnet that has 40 hosts on it. It's either going to be 32 or it's going to be 64. It's those 30 or 62. Because it's all about those powers of 2. This is all binary numbers here. And so 30 isn't big enough, 62 is bigger, but hey, it gives you a bit of space for growth. And so that's what they've done. And so the subnet mask is 255.255.192 or /26. The joys. VLSM. Now, so what that previous example did was you had 1,022 addresses. So this is your 1,022 addresses, basically. And then they said, well, the closest match we've got is 62 hosts per. And so basically what they did was they just basically divided that pie up into chunks. That's what they did. And so each one of these is a subnet, basically. They're all separate. Got a router interface for each, so you can route between them and all that. That's something you need to do when you do subnetting. So that's what that solution was. So as you can see here, you've got your different branch 1, 2, 3, and 4, plus your corporate headquarters. So that was what they needed. Now you'll notice that there's the links between the corporate headquarters and all the other branches. There's actually a /26 network there as well. So there's 62 addresses set aside for these links as well. So that's not very efficient because you only need 2. There's a router on this end and there's a router on the other end inside the ISP. That's all that was really needed for those. And so you've actually wasted a lot of addresses. And so it's easy. All the subnets have the same mask. That's easy. It's certainly easier to not make mistakes with that kind of addressing scheme. But there's 1,000 addresses available. That's a lot. And they didn't actually need that many. 10 subnets of 40, they only needed 400. And so they've actually used most of that 1,000 when they really only needed roughly 400. So it's not particularly efficient. And so VLSM which stands for variable length subnet masking, you could have actually tailored every subnet exactly to its own needs. Instead of having the same, one size fits all, which is basically what that, with my poor drawing, what that shows. And so given the topology, 7 subnets are required. That is 4 LANs and 3 WAN links. And the largest number of hosts is in building D with 28 hosts. So here we've got 28 hosts. We've got another subnet here with 15, another with 20, and another with 25. And so these, of course, these are the WAN links, wide area network links, and there's only 2 hosts required on those. And so we can actually tailor each subnet to their own needs. Now, when it comes to this, they're all going to be the same. They're all going to be /27, because the options, of course, are 30 hosts or 14 hosts. None of them are happy with 14 hosts. This one, by a very small margin, and so they all need to have that 30 host option available to them. So that's why they're all /27. But these would not need /27s here. You could use that /30. That's what that /30 is all about, is WAN links, and that you could use those on those subnets and use them quite happily. Now, however, the point-to-point WAN links only require 2 addresses and therefore waste 28 addresses each for a total of 84 unused addresses. Applying a traditional subnetting scheme to this scenario is not very efficient and is wasteful. VLSM was developed to avoid wasting addresses by enabling us to subnet a subnet. Now, so they're saying, so the calculation here, at least for these subnets, is how many hosts per subnet. And so 2 to the power of 5 minus 2 equals 30. So that's why we're using 27-bit mask, means that there's 27 bits of host address. There's 5 bits left for host number, 27-bit network address. So applying a traditional subnetting scheme to this scenario is not very efficient and is wasteful. Also, to me, 28 hosts is very close to that 30 hosts. Not a lot of growth space there. So even if you applied 10%, that fails on that. 10% growth. So, you could probably give this a larger subnet and be very happy with it. Anyway, so the left side displays a traditional subnetting scheme, which is what I drew there. All the subnets get the same number of hosts. Here, we can basically divide it up. And then you've got actually the possibility of 1, 2, 3, 4, 5, 6, 7 subnets with that number of hosts. And these can all be used for the WAN links. And so we only needed 4 of these. And so this actually gives them 3 spare that they could actually use to expand the company, and without having to redesign the entire addressing scheme again, leaving a bit of space. Or, as I suggested, maybe combine 2 of these together for that for building D, because it's very close to its 30 limit. You could actually supply 62 to this subnet, and these could all quite happily get away with 30. And so just leaves a bit of extra space. So left side displays the traditional subnetting scheme, while the right side illustrates how VLSM can be used to subnet a subnet and divide the last subnet into 8/30 sub-subnets, I suppose. When using VLSM, always begin by satisfying the host requirements of the largest subnet and then continue subnetting until the host requirements of the smallest subnet are satisfied. That's the easiest way of avoiding screwing up the calculations, basically, starting from biggest and going to smallest. And so here, as we said, we've got, well, they're stuck with a /27, that's fine. But as I said, I'd be tempted with a /26 in this subnet. And these have all got those /30s that I was talking about, so much more efficient. Okay, so using VLSM subnets, the LAN and inter-router networks can be addressed without unnecessary waste, as shown in the diagram below. So that all works very nicely. That's just a bigger picture from the other one. So structured design. So IPv4 address Planning. The IP network planning is crucial to develop a scalable solution to an enterprise network. To develop an IPv4 network-wide addressing scheme, you need to know how many subnets are needed, how many hosts a particular subnet requires, what devices are part of the subnet, which parts of the network use private addresses and which use public, and many other determining factors. Examine the needs of an organization's network usage and how the subnets will be structured. Perform a network requirement study by looking at the entire network to determine how much area will be segmented, determine how many subnets are needed and how many hosts per subnet, determine DHCP pools and layer 2 VLAN pools. All right, we're nearly finished, guys. Device address assignment. Within a network, there are different types of devices that require addresses. So end user clients, so host PCs, laptops, mobile phones, tablets. DHCP is a good plan for those because it reduces errors and it makes less work for the support staff. IPv6 clients can obtain address information using DHCP or SLAAC. Servers and peripherals. Typically, you would have a static IP address for those devices. So printers, servers, often will have a static. The other option is actually you can do a reservation. Have we done server at all yet? Windows Server? Okay. You can actually do a reservation. So you actually learn what the MAC address of each of these devices is. And then in the DHCP pool, you can actually assign an address that they'll always get from DHCP. So that's another way you can do it. Servers that are accessible from the internet need to have a public IPv4 address, maybe using NAT. That's what I was talking about earlier. Intermediary devices are assigned addresses for network management, monitoring, and security. And so again, remote management for switches and routers and things like that, all very useful. And of course, gateways will of course need to have IP addressing as well, and that will certainly need to be static most of the time. When developing an IP addressing scheme, it is generally recommended that you have a set pattern of how addresses are allocated to each type of device. Okay, we're pretty much at the end of the chapter. Yay! So, what's in this chapter? Bit of a recap. So, of course, IP addressing structure consists of a 32-bit hierarchical network address that identifies a network and host portion. Network devices use a process called ANDing and use their IP address and the subnet mask to identify the network and host portions. Destination IPv4 packets can be unicast, broadcast, and multicast. There are globally routable IP addresses as assigned by IANA, and typically you get from your ISP. And then there are 3 ranges of private IP addresses that cannot be routed globally, but can be used anywhere by anyone at any time. They reduce large broadcast domains using subnets to create smaller broadcast domains, reduce overall network traffic, and improve network performance. When we're talking about domains, there's broadcast domains, there's yes, and the like. The smaller these domains are, typically the better. And so collision domains as well, they're better as well when they're smaller. Now we don't have to worry about them much because of switches, but yeah, the smaller they are, the better. You can create IPv4 subnets using one or more of the host bits as network bits. However, networks are most easily subnetted at the octet boundaries. Larger networks can be subnetted at the 8/8 or /16 boundaries. You can use VLSM to reduce the number of unused host addresses per subnet. VLSM allows a network space to be divided into unequal parts. Always begin by satisfying the requirements of the largest subnet. Continue subnetting until the host requirements of the smallest subnet are satisfied. When designing a network addressing scheme, consider that you have internal, DMZ, and external requirements. Use a consistent internal IP addressing scheme with a set pattern of how addresses are allocated to each type of device. There's the logo. Hallelujah. So that was chapter 11. Of course, Chapter 12 is basically the same topic, but for IPv6. Now, sort of IPv6 is different, but it's also better organized because they learnt from their mistakes with IPv4. So that's what we'll be talking about in the next time. Have a nice day.